Let's get going. Uh, we have our midday keynote coming up, and I have my good friend Prith Banerjee, my KGP alumni here. He's a CTO of ANSYS. He also has written a book recently that some of you might have already seen. He's going to come and introduce our keynote speaker. So let me not spend much time on it. Prith, can you come up here?
Thank you very much. Very, very good afternoon to all of you. It is my absolute pleasure to introduce a very, very good friend of mine from the EDA industry, Anirudh Devgan, to give the keynote speech. Anirudh is the president and CEO of Cadence. He's also a member of the board of directors since 2021, but he has an amazing record. Previous to his CEO position, he was president and also EVP at Cadence. He took over the job from Lip-Bu, and Lip-Bu, as you know, is a phenomenal leader in Silicon Valley, and he single-handedly picked Anirudh. He recruited him to Cadence a few years ago to take over the CEO role. And prior to Cadence, he was EVP at Magma Design Automation. Many of us know Magma. Rajiv Madhavan's company is another very, very exciting entrepreneur here. And again, Rajiv, a person that I know for many, many years, personally recruited Anirudh to lead the activities at Magna. And before that, he spent many, many years at IBM Research. He has his undergraduate degree from the lesser-known IIT, IIT Delhi, which is ranked lower than IIT Kharagpur. And he did his master's PhD from Carnegie Mellon with a very famous professor, Ron Rohr, who is again somebody that I know. And Ron has told me many times that he is his best PhD student ever. So coming from Ron, that is a big, big accomplishment. Anirudh is one of those people who are deeply technical. He has a PhD. Most people who have PhDs end up in roles as a CTO like myself. Few people become CEOs of companies at the size of Cadence. Not only has he got technical contributions, he's got many, many, many publications, 27 patents, he's a fellow of IEEE, the kinds of accolades that people like CTOs get, but he is also the CEO of Cadence. He is well known in the area of parallel and distributed algorithms for simulation, and he has literally taken Cadence on a fantastic journey, moving away from the core area of EDA into very, very exciting areas. So I've asked him to speak around the future directions of EDA, the challenges and opportunities, and he's going to speak for about 15 minutes, and then I'll engage him in a Q&A session for about 5 minutes, and then the rest we'll ask from questions from the audience. With that, Anirudh, please come to stage.
Hello, everyone. Thank you, Prith, for the nice introduction. It's good to be here. Actually, this is my first time at the IIT Bay Area conference. And I was thinking, man, first of all, keynotes are always hard, right? I'm sure you have been to enough keynotes, and I've given my share of keynotes. They're always hard because some people are like super experts. So some of you already know everything I'm going to say and more. And some people, are not interested or they're not in the area. So keynotes are hard in general. And then, of course, IIT audience is one of the smartest audience you can get. So I'm sure, so take it easy on me, okay? So now IIT, of course, like Prit said, I'm from IIT Delhi. And not only I went to IIT Delhi, I grew up in IIT Delhi. My dad joined IIT in 1961 when it was formed. So all my 20 years in Delhi, I lived in house cast in IIT Delhi. And my wife's father was also a professor in IIT Delhi. He also joined in 61. So I am as IIT as you can get. Yeah. And, yeah. And of course, the best thing was that my dad, this is a different story. His last name is different than mine, so the best thing was a lot of people didn't know that my dad was a professor. So that's a good thing. And we won't talk about rankings though, okay? Yeah. So I think let me give you a preview of what we are trying to do, okay, in Cadence. Some of you may already know. I know some of you are well aware, and some of you are customers. Some of you may not be as aware of what is this EDA and what's happening in the EDA industry. So I'll give you a preview, and I won't talk for too long, and then please ask me any questions. And then if you want to get hold of me in general, so my email is straightforward. So my last name, Devgan at cadence.com or Devgan at devgan.com. There's a story there. Actually, Ajay Devgan tried to buy the domain devgan.com from me, but I didn't sell it to him. Okay, so this thing works. Okay, this way. So a little bit of overview of Cadence. So Cadence is about 10,000 people. We are in all the main kind of high-tech centers in the world. About 40% of our revenue is invested in R&D. Okay, so that's one of the highest investments in R&D for any kind of S&P 500 or NASDAQ 100 company. So we have about 6,000 people in R&D. Maybe at least half of them have graduate degrees. And then we have about 2,000 people in what we call AEs or customer support, but they're also engineers. So out of roughly 9,500, 10,000 people, about 8,000 people are engineering. Okay, and so we have a big investment in R&D. We also have it's a very profitable company. So we have about 40% operating profit, about 90% gross margin. So this is a good thing about software. So the key thing was, is the revenue growth. But this year, our guidance to Wall Street is a revenue growth of 17% and profit margin of 40%. So there are only a handful of companies in the world that can generate that much revenue growth and profit. So if you plot like Cadence stock, okay, of course that's one indicator of performance, but it's an important one. If you plot it over the last 5 years, it's one of the best performing stocks in S&P 500 or NASDAQ 100. Now, but the key thing is, EDA always, I think it's critical to, and there's a lot of digitization and also role of semiconductors became more and more important. Actually, I was in DC a couple of weeks ago, and there was this CHIPS Act, and even US government is talking more and more about semiconductors, so, which is great to see. And actually, I gave a talk at an Indian conference also. Actually, Indian government also has a huge investment. EU also has a huge investment in semiconductors. Of course, China had it for several years. So we basically, what Cadence does, if you don't know, we design software products, mostly software, for the design of semiconductors. Okay. And then what is interesting right now in the last few years, our growth rate used to be maybe 5 years ago, maybe 6, 7%, and now, of course, well into double digits. So the other exciting thing is that a lot of system companies are designing semiconductors, and we are also trying to move to the system level. So about 45% of our customers right now are system companies, so hyperscalers and car companies and things like that. Okay. So, one of my goals is to improve our ROI, okay? ROI, I don't mean return on investment, okay? That's already pretty good, like I told you. But return on intelligence, okay? So, yeah, because we have a lot of smart people in our industry and Cadence and EDA, and the question is, can those people do other things apart from just, silicon, which is still our core business, okay? So I'll talk to you a little bit about that. So the way we look at the word, and this is all, you know all this, is in three circles, okay? So the outer circle is the data circle, then the circle within that is the system circle, and the circle within that is the silicon circle. Okay, perfect example is like an electric car. So you have all the navigation data, and then you have the actual physical car, the hardware, software, the electrical and mechanical, and then you have the chips that drive the car. Okay, so this is happening in all industries. Okay, car is one example. Same thing in data center or mobile or you name it. Okay, and so when we want to grow, it's very important to grow in your area of expertise. And it's very important to figure out for any company what they are really good at, okay? Because everybody wants to grow, so we have to figure out what is your core strength. So in terms of Cadence and EDA, the core strength is what we call computational software. So this is CS plus math. So if you know about EDA, it has probably the most sophisticated algorithms in terms of numerical analysis, Boolean algebra, whatever you can imagine. And it has been traditionally applied to silicon, which is, so the red arrow here is computational software. And if you apply it to silicon design, that's EDA and IP. And then the next circle is system. So if you apply it to there is system simulation. I will talk a lot more about system simulation. And you apply CS and math to data, of course, that's AI and data analytics. Okay. So not only we want to do well in EDA, and we are doing pretty well in our core business, but also into systems and data analytics and AI. And of course, these are horizontals, and they can be applied to multiple verticals. But I think, again, that's the other important thing for me is the expertise, okay? We are a technology company, has to be built at a horizontal level, okay? Because that's what we have to do in a scalable fashion. And then, of course, it can be applied at multiple verticals. So you need both expertise, but horizontal expertise, in my mind, is super critical, which is computational software or certain algorithms, and then you can verticalize it. So sometimes people confuse what is horizontal and what is vertical. So it's very important to make sure that you have strong foundation horizontally and then apply it to multiple verticals. Okay. Now, I will skip some of these slides. I mean, the good thing is silicon is in a renaissance for the multiple reasons you know. It's about $500 billion industry. This is our customers. And it is expected to double in the next few years to about 1 trillion. And of course, it is used in almost all aspects of digital transformation. And good thing is almost all chips that are designed in the world use some form of Cadence software. Okay. And then we have these other systemic drivers. I can, you know most of this. I can talk to you more if you want. But one of the big things is system companies doing silicon, and there are a lot of reasons for it. Okay, just to say high level, and we talk to all these big companies. So, and you say, like, why are you doing silicon? So there are three main reasons that I saw. Okay, so first is for customization. Look at Tesla, right? They designed their own self-driving chip, and they can optimize versus what NVIDIA was doing. And it's much more efficient in self-driving. So there's always some customization they do it for. Second reason is for schedule. If you're going to launch a product certain time of the year, or you want to control your own schedule. And third thing is if there is enough volume, which of course there are enough cars sold in the world or enough data centers, then it is economically better to do your own chip. Okay, so that's why you see this big resurgence. And there are other things we can talk about, but I think that's an important trend. Okay. Now, the other thing is when you come from the system level to the chip level, and like 45% of our customers are system companies, the first thing you see, if you open up your washing machine or car or whatever, is not the chip. You see the board and the package, and then the chip. So it's very important, not just the chip level, but to do innovation at the board and package level. And this has been historically ignored because real men and women used to do chips, okay? But now I think the board and package becomes super critical. And we have a lot of initiatives in that. Actually, Cadence is in a very good position in that space, okay? So, and we also have partnership with some companies, a very good company like Dassault, who are leaders in mechanical design and this whole hyperconvergence of mechanical and electronics. Okay. So overall, I think it's in a growing market. So semi is growing, system is growing. I mean, you know all this, so it's good to be in this space. Okay. Now, you know, when I was in IBM, you know, Prit talked about when I was in IBM, I used to work with Bob Denard. I don't know if you know Bob Denard. You know Moore's Law, right? So the actual science behind Moore's Law is done by Bob Denard. Okay, he's genius. He's also the inventor of DRAM. Okay, IBM invented like half the things. They didn't productize all of them, but so I think even 10, 15 years ago, when I left IBM, it was clear that Moore's Law is slowing down, right? And you know, the classical scaling is done for a long time. And if you look at last 10 years, most of the scaling is not the chips getting necessarily faster. I mean, they are getting faster, but you put more things on the chip. So instead of one CPU, you have 8 CPU, you have neural engine, you have AI engine, GPUs. So it's more integration last 5, 10 years. And I think that, you know, so the use of multi-core is super critical. And I think the hardware, in my opinion, is way ahead of the software. Because hardware always produced all these, even now, GPUs, AI, CPUs, but the software guys were not able to use them. I don't think they still use them well. So it's very important for the software to keep pace in what the hardware is doing. And also very important for the next generation of integration is now system on a package. So it's just a continuation of like 3D IC. And actually there is a paper by Subhashish from Stanford that he did some analysis, he's also IIT, I think, okay, that 3D IC can extend Moore's Law by 7 generations. Okay. So I don't know whether it can extend by 7, but if you take it half, it can extend by 3 or 4 generations. And Moore's Law itself, you know, we are at 5 mostly, a lot of design at 3. So there will be 1.x node, there will be 1 nanometer. So there are at least 10 years of Moore's Law, at least 10 more years of 3D IC. So there is still a lot of more work to be done. Now from a computational, what we call computational software or EDA standpoint, you know the traditional EDA, and then we have to evolve to meet this demand of next 20 years. Okay. And one of the things we have done is a lot of use of parallelism. I won't go into the detail. Actually, we have a lot of advanced parallel algorithms over the last 10 years. And of course, now it's fashionable to call it cloud. Okay. But this is not just decoupled algorithms. Okay, that's trivial to parallelize. But these are coupled algorithms that are parallelized over a network of machines or the cloud. Okay, so there's a lot of things we can do there, and I won't get into the details. I want to talk to you more about what we can do in the future. Okay. So of course, one big thing people talk about is AI, right? And what is the application of AI to all verticals. So let me talk to you a little bit about that. So first thing with AI is, I think, I don't know if you follow Michael Jordan, not the basketball player, the professor at Berkeley. So he says, stop calling everything AI. Okay, this is a big problem right now. It's like a super buzzword, so everything is AI. What I joke around with people is that these days becomes so much of a buzzword, which is not a bad thing, that even an if statement is AI, right? It's artificial, it is somewhat intelligent, okay? And then if you have an else statement after that, okay, then it's reinforcement learning, because you learn from the if statement. Okay. So this is the problem now, whatever you say, and this is like Hinduism also, right? They say, well, everybody is a Hindu, because this is how you take over the world, not that that's the purpose of Hinduism, but like the Jews were Hindus, and then the British came and said, no, you are Jews, you are not Hindus. Okay. So this is the problem with AI. Everything, everybody claims they are expert in AI. Okay. Now the question is where to apply AI. Okay, so my simple explanation is that AI, of course, is good for a lot of things, and it's more like pattern matching or curve fitting. So people don't like that kind of word, you know. But if you ask my dad, who's a math professor, he'll say AI is generalized curve fitting. But so what it is, if you look at a function, y is equal to f of x. Give me 1 minute, okay? So x is the input, you know, y is the output, right? F is the function, okay? Now, of course, you can observe the function, you know, you don't just the output, you can observe within the function. But for a data-driven approach, what that means is you observe x and y, and you try to determine f, okay? That's the data science, okay? Now, the other part is, and this f can be like a simple function like, you know, linear or polynomial, or it can be nonlinear differential equations with a lot of state, okay? So this f can be anything, okay? But you can, of course, learn f by input-output observation, okay? Now, that's good and works in a lot of cases. But there also you can discover f, you know what the form of f is, okay? So that's inside out. You know, if you know what f does, whether using physics or chemistry or biology, you can do actual simulation or you know, what actually f does. So I think it's very important to combine these two. You know, the inside out, which is in which you know what f is, and some cases you don't, and outside in, where it's purely data driven. So just applying outside or just inside is not, so my opinion is both is good. So now we have traditionally done a lot of inside out in EDA and a lot of math disciplines, but we need to complement that with outside in, okay? And one example of that is even chip design, right? So chip design, we have these products that will model the physics of the chip, and you design the chip, but it will have a lot of variables, okay? So for example, you know, worked with one customer, they're running our software, it has a lot of variables. And I think this outside-in application is useful for optimization, in my opinion. Okay, we can talk about this as a long, these are all, you know, long discussions. But to give you example, this outside-in view, so we have 17 variables. Now, some of them are design variables, or 20 variables, 100 variables, whatever you have. Some of them are design variables, some of them are tool options. And to actually determine the right set, to optimize this right set is a very difficult problem. And that's where we are applying AI in our case, okay? And so we call it reinforcement learning. And there are multiple ways to do that. I had a slide here, which I think is not there, okay? But basically, I think instead of human doing, right now what happens is when you do chip design, you know, the human is finding this combination in this multidimensional space. But we can use reinforcement learning, and we got very, very good results, okay? Because you are, so my opinion is if something is well-defined mathematically, you know, like placement, there are well-known ways to solve it mathematically, then AI has limited value. But if something is not well-defined mathematically, and especially in EDA, we were not good at transferring knowledge from one run to the next run. So you look at all our software was optimizing a given set of conditions, but whereas the user is running one run, then they change something, they run another run, they change something. So that's where I think AI can have a phenomenal effect. And you know, I won't go to the details here, but we are getting remarkable results of applying AI to optimization, which is the outside-in view. Okay. Now, the other thing I want to emphasize, I'll skip some of the PCB stuff. So the other thing I want to emphasize is the system level stuff, right? So 45% of our customers are system level. 3D IC is a big thing. Lot of, you know, if you go to 3D IC, one of the big things is thermal simulation. You know, this, if you talk to TSMC or these foundries. So not only we have to model all these system level thermal effects, power effects, and a lot of the math is very similar to chip design. You know, like finite element analysis is a big thing at system level, or CFD, computational fluid dynamics. But if you look at the math, it's very, very similar to what we have done in EDA all these years. So about 5 years ago, we started a big effort to do system simulation. We have about 1,000 people in R&D working on that, okay? And that is natural synergy with our, you know, SDA along with EDA, okay? And then when we go into SDA, So when we go into this system level, I mean, there's a lot of data that can be applied, a lot of simulation that can be done. So there are 2 or 3 big areas. So finite element is a big area, okay. CFD is a big area. And this is like $8 to $10 billion market in all kinds of simulation. You know, when you simulate your car or, you know, jet engines, you know, this is a big thing. And there's not that much use of computation in these areas compared, I mean, there is some, but not compared to the chip level. Because chip level, the amount of, it's so expensive, so amount of computation was much, you know, we talk about digital twin at the system level, at the chip level is more like a digital mother, okay? Because it has to be so accurate if you're going to spend millions of dollars fabricating the chip. So that, all that can be applied to the system level, especially in digital twin, okay? So we did an acquisition recently for digital twin, especially for data centers, which is pretty exciting, called Future Facilities. And it takes the actual building, combines CFD, ACs, vents, and gives you a complete living representation of the data center that you can optimize. Again, the math is very similar, okay. So we have a lot of efforts in like finite element and CFD, but not only we want to disrupt like existing markets in simulation, which is these 2, there's also emerging market in simulation, okay. And one of the most exciting emerging areas where this CS plus math can be applied is, of course, biosimulation. So we recently acquired OpenEye, which is a SaaS-based platform for drug discovery and biosimulation. And I'm super excited about that, okay? Because if you look at that stuff, you know, if you look at transistors, we'll have a physics-based model of a transistor, and then we will do all kinds of simulation, you know, and we are leader in circuit simulation, inspector and all that. So we do all kinds of millions and billions of transistors you can simulate. If you look at molecules or biosimulation, it's very, very similar. So you can do a physics-based model of the molecule, and then you can simulate the interaction of several 100,000 molecules. That's what they do now. A few 100,000 molecules can give you a lot of stuff. So I'm super excited about applying this in general, like CS plus math to the system domain, both like traditional simulation areas and new simulation areas. And then there is a natural synergy to our core business, which is still the most important thing for us, is to do well in EDA and core business, but at the same time, you know, you expand into synergistic areas. So I'll stop now. I can talk forever, you know, and of course we are hiring a lot. We have a lot of openings. So if you know somebody who's interested, or if you are interested, come join us. And thank you again for your attention. Yeah.
Thank you very much. We'll take a few questions. So unfortunately, we'll not have time for too much audience Q&A. I will do a few, and then he will stay around so you can ask your questions. Phenomenal presentation, Anirudh. I mean, you literally, I was going to ask you what the future of AI ML, the future of high-performance computing, cloud, and some of the other areas. You have literally covered them all, so you did a great job. One just broad question I want to ask you is, in the world of EDA, right, where you and I both studied like 30 years ago, originally it was custom design, where the designer had to enter rectangles, right? But the complexity of that thing was limited to maybe 100,000 rectangles. And so people came up with gate level design, and you did place and route to improve the productivity. Then when people said, well, that gate level netlist is too complicated, you move higher level, right? In RTL, VHDL, Verilog, push a button, synthesize the netlist, and so on. So now the question I have is, you shared this phenomenal vision of sustainable things, right? I mean, literally the car, the automobile, right? And essentially they have these different engine blades, etc. Then they have the electronics and so on. How far are we from a truly system level synthesis of electromechanical systems? I mean, I gave a DAC panel recently, last month, and I've talked about those things. Just your thoughts. I mean, are we like 10, 20 years away, or is that something that we will never get to?
Well, that's a very difficult question. I mean, I think, yeah, these things are, see, okay, this is a very good point. I mean, of course, simulation is critical, but what is even more critical is optimization, okay? So when we say computational software, of course, EDA has a huge history of optimization. is probably the most optimized set of algorithms. If you look at place and route or something, the amount of optimization there is intense. And whereas that is not there to that extent at the system level. And EDA has, or at the bio level, they can barely analyze the molecules. Optimization would be drug development or something. So I think there's a lot of potential, but there's a lot of steps that need to be done. And actually Alberto, who's on the board, gives a very good talk that you have to have, increase the level of abstraction. So you need to have languages to describe that. And also a lot of times what is missed is verification. Because when you go to a higher level of abstraction, like when we go for transistor to gate level, you need to make sure those two are equivalent. So I think at the system level, and the same thing with self-driving and all these things, the validation of how correct it is as important as optimization. But I think it's still very, very early. And I think a lot of people don't sometimes apply principles that are not fully developed. But it's a good area because, all these things have huge effect, right? Whether it's cars or planes or biology. So we are excited to take the learning in EDA and apply it. But EDA also took like 30, 40 years to go through this journey. So.
The next question I will ask is, I am super excited about your acquisition of OpenEye. As you said, the whole drug discovery area is so premature, and people are still doing their designs in the test tubes and so on, and that area can really benefit from advances in EDA. EDA applied to healthcare, and so great move on your part. Thank you so much for a fantastic talk. As a token of appreciation, I want to take my life's journey, which I've put into this book called Innovation Factory, which talks about how large companies like Cadence and others can pursue long-term innovation. It is my honor to give you a signed copy of the book. Thank you so much.
Thank you. It's good. Wow, looks great, man. Thank you, and please contact me. Sorry, these things are short. Anything I can do to help. And one last plug, okay. We also, 6 months ago, I set up a Cadence Giving Foundation. Okay, now we are big enough that we need to help the community. So it's a relatively significant financial investment by Cadence. So we have 3 areas of focus, DE&I, education, and climate. So if there are opportunities we can help in the community, we are always open. Okay, thank you.